Hello, students. It's Dr. Church, and today we're going to talk about one of my favorite subjects in earth science as we wrap up our year, and that's astronomy. We're really looking at the Earth within the solar system and within the universe. So I think that's pretty cool. I remember when I was in, I guess, middle school, and we studied the little astronomy unit. And I don't know how they did this, but we built a telescope and we broke up into groups of students. And one of my jobs was I was polishing a piece of glass into a concave shape to put into a reflecting telescope. Now, let me say I don't think I ever got that thing to work, but it was sure a lot of fun, and I thought it was super cool to do it. So let's go ahead and take a look at some basic early astronomy. We're looking at early astronomy in unit 22 in section number 1. What is astronomy? It is that science that studies the universe, deals with properties of objects in space and the laws under which the universe operates. For as long as people could look up and wonder about our place in the universe, people have thought about this. In around 600 BC to 150 AD, we have what's called the golden age of astronomy. This is when some of those early thinkers were applying math and science concepts, trigonometry, and just basic principles of science. Not really looking at it from some of the other philosophical points of view, although the Greeks used a lot of philosophy in their early work. But these are people that are trying to discern things scientifically. Some of the earliest calculations done, Eratosthenes 276, one of the first accurate measurements of the size of the Earth. If we look at some of the work that he did, um, you'll see there's an angle here. He actually was able to go to a couple of different cities and he measured the angle at which the sun's rays encountered the surface of the earth, and he determined that angle to be 7 degrees. And then based on the distance between those two cities, he calculated that the arc angle that he had measured was about 1/50th the diameter of the Earth as a sphere, and so he extrapolated that number out to about 39,400 kilometers, which is actually pretty close to the actual measure of the actual circumference of the Earth, rather. Hipparchus, he cataloged 850 stars. He measured the length of the year fairly accurately within a few minutes and even predicted some lunar eclipses. Now, as we look back at some of this early history, you've got two basic models. Of course, the first was the geocentric model. This was what the Greeks followed. It has the Earth at the center, with the sun and moon and other planets kind of orbiting the Earth. Now, when we think about this, we think, well, that's silly. Everybody knows that the solar system is heliocentric, or with the sun at the center, with the Earth and the planets revolving around the sun. But when you think about it and just look at it observationally from those very early observers, it does appear as if the sun and the moon and the planets are revolving around the Earth, rather than the other. So it really was a shift in thinking that wasn't going to come until a little bit later. Ptolemy, he outlined the movement of the planets, and he was very interested in watching the planets as they went around the Earth, or what he thought they were going around the Earth. If we look at that, let me grab my little circle here, and if we look at the way that he was looking at the planets as they went around the Earth, if we look here, here's the Earth as he's watching them. They do look as if they're moving right around the Earth, but and he plotted that as circles, the perfect geometric shape to the Greeks, and he but he noticed something very interesting. It looked like that the planets were not only moving this way, but they were circling what was called retrograde motion. And he called these the wandering stars. When he looked up, now obviously he couldn't see the planets the way that we see the planets now through telescopes. He only saw points of light, and so he thought those were just stars, but he noticed that against the background of the universe that they seemed to be wandering around. They made little circles within their orbits, and eventually, of course, we discovered those were the planets. Um, we often hear about what's called the Copernican revolution. Well, what is that? Nicholas Copernicus, Polish, 1473, he proposed the model of the solar system with the sun at the center. So no longer was the geocentric model followed, but he proposed this. That was not a very popular thing for some folks at the time and was difficult for him historically, but he said that the Earth is just a planet. It's not, in fact, at the center, that the sun is at the center, and then this allowed some of the mathematics to work out. And you often wonder, well, why did they ask these questions? Why did they think one thing or the other? They were trying to make sense of what they observed, and they were trying to put the mathematical equations to predict the motion of the stars, the sun, the moon, the earth within the motion. And so depending on how you look at it, the model that you establish determines the accuracy of the model, and that of course is a big deal in science. We want to predict things accurately and with a high degree of precision. Tycho Brahe, he's a Danish astronomer. He actually built some instruments to measure locations of the heavenly bodies. He was especially interested in Mars, and he made some of the most accurate observations and predictions of anyone up to his time. He spent 20 years of his life plotting positions of the planets. He spent a lot of time looking up. You got to remember that this was the time before computers and videos and things that we could just set up and go back and look at it and fast forward later or whatever. He was actually making this data, these observations himself. If you've ever just gone out and sat at night and looked at the stars, you can see how challenging that might be at times. Well, following Brahe was Johannes Kepler. So Kepler was one of Brahe's students, and he came up with what was called Kepler's 3 laws of planetary motions. He's the one that said no, that the planets are not actually following circular paths around the Earth, but are in elliptical paths around the sun. He said that they revolved around the sun at varying speeds, that the planets are not all moving at the same speed. Now, we sitting here on the Earth, we don't notice any movement at all. We don't feel that. Objects that moving at a constant velocity, we only feel accelerations. Now, if the Earth began to speed up or slow down drastically, definitely we would feel that. But he said that the planets are varying in their speed, and that there was a proportional relationship between a planet's orbital period and its distance to the sun. So we're not always the same distance from the sun, and those are fairly big numbers compared to what we normally think of in terms of distances that we travel on the Earth. Now, what is an ellipse or an elliptical shape? You've probably studied this in mathematics, but if you have not gotten into your geometry yet, it's that kind of oblong or maybe an egg-shaped type circular, but it's odd shaped, right? It's the oval shaped path. Now, we came up with what's called the astronomical unit, which is the average distance between the Earth and the Sun, which is about 150 million kilometers, okay? The Earth's orbital speed. Now, this is one of the questions I always enjoy asking students in classes: how fast are we going through space? Like, how fast do you think we're moving? Again, it seems like we're not moving at all. But in fact, if you trace the distance that the Earth travels around the sun in 1 year, in 365 days, and you do the calculations, the Earth is moving at over 66 1,000 miles per hour. And that is extremely, extremely fast. Well, following Kepler, Galileo is probably one of the most famous, if not the most famous, Italian scientist. His contributions really are, you can't be overstated. He developed his own telescope, and with the telescope, he began to make some very important observations. Well, what were some of his observations? He's the one to call out Jupiter's moons. Now, we know that we have one moon. Well, Jupiter has four. And these are satellites that actually orbit Jupiter, just like the moon orbits the Earth. He said that the planets are circular disks, not just points of light. And eventually we know that the planets are spherical in shape. They're not just circular disks, but before Galileo, they just were points of light in the sky. Venus has phases, just like the moon does, and so it's moving within. There's a shadow that's cast on it, and of course we know that that shadow on the moon is created by the Earth coming between the sun and the moon. The Earth's the moon's surface rather is not smooth. You can see up there if you look at it with a telescope or some other magnifying device, you can begin to see some dark spots on the moon, and eventually he discerned that that the moon was not in fact smooth, and that the sun has sunspots. These are sunspots on the moon. These are the little dark, I'm sorry, on the sun. These dark spots on the sun, okay, which we know are sunspots. But with the naked eye, you certainly can't see that at all. You wouldn't want to look at the sun anyway. It would destroy your vision just very, very quickly. Ptolemy, the Ptolemaic system, talked about the orbit of Venus between the sun and the earth, and so that would explain that shadowing of Venus. The Copernican system, Venus orbits the sun and all the phases are visible from the earth. And then Galileo comes along and says Venus goes through phases similar to the moon. So we see these historical movements and development. Well, probably the most famous of all our scientists is Sir Isaac Newton. He formulated the universal law of gravitation. If we take physics, you'll study that and you'll see how that works. He talked about how the force of gravity is a function of the mass of two objects, and gravity is a function of the fact that you have two masses from some distance, and that all objects actually do exert gravity on all other objects. And this began to explain the movement of the stars and planets and things that we see. And so he was putting the physics behind that. Gravity, it's the influence of gravity that explains this elliptical motion that we see, and the fact that the Earth's not always at the exact same distance from the sun. And when we start to look at the motions of the Earth, we see that there are two main motions: rotation and revolution. But then there's another motion that we don't often think about, and that's what's called precession. It's like a top spinning. When a top spins and begins to slow down and sort of tip over, it'll make this circular motion this way. That's precession, and the Earth actually does that, even though its axis remains remains constant. It actually precesses about this axis of rotation, but it moves very, very slowly while it's doing that. It takes about 26,000 years to make one precession. Well, what is rotation? Well, that's just the turning on the axis, and we know that the time it takes for the Earth to make one rotation is 24 hours. A sidereal day is the time it takes for the Earth to make one complete rotation with respect to a star other than the sun, which is just a little bit shorter, 23 hours, 56 minutes, and 4 seconds. So there's just the regular solar day, and then there's the sidereal, I think, day. I think I'm pronouncing that wrong. And then, of course, the revolution is the motion of a body, such as the planet or a moon along a path at some point in space. So the Earth is rotating on its axis, but it is revolving around the sun. And there's 2 points on that revolution around the sun: the aphelion, which is in July, when the Earth is furthest from the sun. We know it's not always the same distance. And the perihelion in January, when the Earth is closest to the sun. And we know that seasons are caused by the tilt of the Earth, not the fact that it's closer or further away. Okay, well that's our look at the early astronomy today and of some major astronomers and some of their discoveries. I hope that this has been interesting. I hope you've learned something about one of my favorite subjects, which is astronomy.